Alright, today we're going to study containers in the cloud. In this section of the course, we'll explore containers and help you understand how they are used. Infrastructure as a Service, or IaaS, allows you to share computer resources with other developers by using virtual machines to visualize the hardware. This let each developer deploy their own operating system, access the hardware, and build the application in a self-contained environment with access to RAM, file system, networking interface, etc. This is where containers come in. The idea of containers is to give independent scalability of workload in PaaS and an abstraction layer of the OS and hardware in IaaS. A configurable system lets you install your favorite runtime, web server, database, or middleware, configure the underlying system resources such as disk space, disk I/O, or networking, and build as you like. But flexibility comes with a cost. The smallest unit of compute is an app with its VM. The guest OS might be large, even gigabyte in size, and take minutes to boot. As demand for your application increases, you have to copy an entire VM and boot the guest OS for each instance of your app, which can be slow and costly. A container is an invisible box around your code and its dependency with limited access to its own partition of the file system and hardware. It only requires a few system calls to create, and it starts as quickly as process. All that's needed on each host is an OS kernel that supports container and a container runtime. In essence, the OS is being virtualized. It scales like PaaS but gives you nearly the same flexibility as IaaS. This makes code ultra portable, and the OS and hardware can be treated as a black box. So you can go from development to staging to production, or from your laptop to the cloud without changing or rebuilding anything. As an example, let's say you want to scale a web server. With a container, you can do this in seconds and deploy dozens or hundreds of them, depends on the size of your workload or on a single host. That's just a simple example of scaling one container, running the whole application on a single host. However, you'll probably want to build your application using lots of containers, each performing their own function like microservices. If you build them the way and connect them with network connections, you can make them modular, deploy easily, and scale independently across a group of hosts. The host can scale up and down and start and stop container, and demand for your app changes or as hosts fail. Okay, understood. A product that helps manage and scale containerized application is Kubernetes. As to save time and effort when scaling applications and workloads, Kubernetes can be bootstrapped using Google Kubernetes Engine, GKE. So what is Kubernetes? Kubernetes is an open source platform for managing containerized workload and services. It makes it easy to orchestrate many containers on many hosts, scale them as microservices, and easily deploy rollout and rollbacks. At the highest level, Kubernetes is a set of APIs that you can use to deploy containers on a set of nodes called clusters. The system is divided into a set of primary components that runs at the control planes and a set of nodes that run containers. In Kubernetes, a node represents a computing instance like a machine. Note that this is different to a node on Google Cloud, which is virtual machines running in Compute Engine. You can describe the set of applications and how they should interact with each other, and Kubernetes determines how to make that happen. Deploying container or nodes by using a wrapper around one or more containers is what defines a pod. A pod is the smallest unit in Kubernetes that you can create or deploy. It represents a running process on your cluster as either a component of your application or an entire app. Generally, you only have one container per pod, but if you have multiple containers with the hard dependency, you can package them into a single pod and share networking and storage resources between them. The pod provides a unique network IP and set of ports for your container and configurable options that govern how your container should run. One way to run a container in a pod in Kubernetes is to use the kubectl run command, which starts a deployment with a container running inside a pod. A development represents a group of replicas of the same pods and keep your pods running even when the nodes they run on fail. A deployment could represent a component of an application or even an entire app. To see a list of running pods in your project, run the command kubectl get pods. Kubernetes creates a service with a fixed IP address for your pods, and a controller says I need to attach an external load balancer with the public IP address to that service so others outside the cluster can access it. In GKE, the load balancer is created as a network load balancer. Any client that reaches the IP address will be routed through a pod behind the service. A service is an abstraction which defines a logical set of pods and a policy by which to access them. As deployment create and destroy pods will be assigned their own IP addresses, but those addresses don't remain stable over time. A service group is a set of pods and provide a stable endpoint or fixed IP address for them. For example, if you create two sets of pods called front end and back end and put them behind their own services, the back end pods might change, but the front end pods are not aware of this. They simply refer to the back end service. To scale a deployment, run the kubectl scale command. In this example, 3 pods are created in your deployment, and they are placed behind the service and share one fixed IP address. You could also use auto-scaling with other kinds of parameters. For example, you can specify the number of pods should increase when CPU utilization reaches a certain limit. So far, we have seen how to run imperative commands like expose and scales. This works well to learn and test Kubernetes step by step. But the real strength of Kubernetes comes when you work in a declarative way. Instead of issuing command, you provide a configuration file that tells Kubernetes what you want your desired state to look like, and Kubernetes determines how to do it. You'll accomplish this by using a deployment config file. You can check your deployment to make sure the proper numbers of replicas is running by using either kubectl get deployment or kubectl describe deployments. To run 5 replicas instead of 3, all you have to do is update the deployment config file and run the kubectl apply command to use the updated config file. You can still reach your endpoint as before by using kubectl get services to get the external IP of the service and reach the public IP address from a client. The last question is, what happens when you want to update a new version of your app? Well, you want to update your container to get new code in front of users, but rolling out all those changes at one time would be risky. So in this case, you would use kubectl roll out or change your deployment configuration file and then apply the change using kubectl apply. New pods will then be created according to your change update strategy. Here's an example configuration file that will create new version pods individually and wait for a new pod to be available before destroying one of the old pods. Okay. So now that we have a basic understanding of container and Kubernetes, let's talk about Google Kubernetes Engine, or GKE. Google Kubernetes Engine is a Google host managed Kubernetes service in the cloud. The GKE environment consists of multiple machines, specifically compute engine instances, grouped together to form a cluster. You can create a Kubernetes cluster with Kubernetes engines, but how is GKE differ from Kubernetes? From the user perspective, it's a lot simpler. GKE manages all the control panel components for us. It still exposes an IP address to which we send all of our Kubernetes API requests, but GKE takes responsibility for provisioning and managing all the control planes infrastructure behind it. It also eliminates the need of separate control plane. Node configuration and management depends on type of GKE modes you use. With the autopilot mode, which is recommended, GKE manages the underlying infrastructure such as node configuration, auto-scaling, auto upgrades, baseline security configuration, and baseline networking configuration. With the standard mode, you manage the underlying infrastructure, including configuring the individual nodes. Let's examine the benefit and functionality of Autopilot in more detail. Autopilot is optimized for production. Autopilots also help produce strong security posture, and Autopilot also promotes operational efficiency. The GKE standard mode has the same functionality as Autopilot, but you are responsible for the configuration, management, and optimization of the cluster. Unless you require specific level configuration control offset by GKE standard, it's recommended that you use autopilot mode. Okay. You can create a Kubernetes cluster with Kubernetes engine by using the Google Cloud Console or the gcloud command that is provided by Cloud Software Development Kit. GKE clusters can be customized, and they support different machine types, numbers of nodes, and network settings. Kubernetes provides the mechanism through which you interact with your cluster. Kubernetes commands and resources are used to deploy and manage applications, perform administration tasks, set policy, and monitor the health of deployed workload. Running a GKE cluster comes with benefit of advanced cluster management features that Google Cloud provides. These include Google Cloud's load balancing for compute engine instances, node pools to designate subset of nodes within a cluster for additional flexibility, automatic scaling of your cluster node instance count, automatic upgrades for the cluster's node software, node auto repair to maintain node health and availability, and logging and monitoring with Google Cloud Observability for visibility into your cluster. To start up Kubernetes on the cluster in GKE, all you have to do is run the command gcloud container clusters create K1. Okay. Oh, no labs. Go directly to quiz. Okay, let's take the quiz. Okay, where do the resources used to build Google Kubernetes Engine cluster come from? Compute engine. What is only 50%? Only 2 questions. What is Kubernetes pods? It's a group of container. Okay. Cool. And then next, what is it? Next would be container in the cloud. Okay, we just did container in the cloud. Next is application in the cloud, and then we'll do this for the next section.